You've been focused on capital omega in your study of trig and in your study of physics. What we're introducing is a new form of math called discrete math that uses little omega. And the difference between them is big omega is radians per second. Little omega is radians per discrete sample, per number. It's hard to wrap your head around, but it's the kind of thing that's going to help you understand quantum mechanics. Let's look at the overall workflow. We're going to start with a science experiment or an engineering project. You're collecting data. You've got a sensor or a transducer that's putting out a changing voltage. Your goal is to find patterns inside that changing voltage. What patterns? Well, the patterns you're looking for are related to the traditional big omega, the radians per second. There'll be an engineering project requirement, or there'll be a hypothesis of a scientific experiment. Big omega, or the collection of big omegas, is used to determine the sampling interval. That's a unit of time in between samples. Capital N is the number of samples that you take. So we've established two parameters of our experiment that have to be determined before we actually take the data: the time between samples and the number of samples. Using the sample interval, you can use that to take this DFT display and turn it into a Fourier series. That's where our omegas actually show as an equation. And then that equation should be able to recreate the linear output of our input. So it's a method of checking our input. So if we start off in reality, we should start with a real number. And we should end with a real number. In between, we're going to fluff up our data with some imaginary information. One of the issues with the hypothesis or the project requirements is, what if you're expecting two identical omegas in our input data? Well, going through this process does not allow us to distinguish between those two omegas. They appear as one in our final output. So we understand T. What is N? N is samples. Radians per sample times samples gives us just pure radians. Radians per time multiplied by time gives us just pure radians. What is a sample? A sample is a thing. It's a series of things. It's not continuous like time. What are radians per sample? They're a kind of angular distance between the numbers. How do we represent discrete? Typically it's with these stem plots. Continuous time we're going to try to represent as a smooth line like this, even though internally inside the computer it's discrete. Here's a discrete version of x2. Now it doesn't have any kind of pattern like that. And then when we try to go back and recreate it in time, we're just going to have a mess. Now, to create this animation of something improper, involves a little omega that doesn't have pi in it. Now, we're going to get back to that coming up. But you have to understand that there are lots of ways to mess up. Here I try to tease out all the differences between big omega and little omega. This line can be expressed as a positive angle or a negative angle. I set up n equal to 6, no phase. So we step around the circle 6 times. Here's n equals 1, n equals 2, 3, 5, 6, 7. We just start over again. So any little n bigger than n is silly. It's just repeating. That's the equivalent of subtracting 2 pi. So now when the gold is on top, it's actually closer to 0. So if you think of this as a negative angle, its positive angle is actually smaller than this positive angle. Phase just splits these apart so that the blue and the gold are always visible. Now, the next section 7 drives us into this animation into even more depth. So let's continue with that. Suppose we're looking for two frequencies in our input data. And these frequencies in time have been translated into little omegas. what kind of spikes should we see? What kind of stem plots should we see in the DFT? Well, the first thing we have to do is subtract 2 pi from both of these. Now we can see right away that there's no 2 pi we can extract from 11 without turning it into a fraction. So to get it into the right form where we have 2 pi in the numerator and n in the denominator, we know that n is 26, not 13. So we know that since omega 1 is 11 and it's less than the midway point 13, that it's going to be a pattern and be the leftmost spike representing omega 1. The question is, where's omega 2? Omega 2 is 16 and it's greater than 13. So where is it going to appear on the DFT? Well, before trying to answer that question, let's go back up here and look at this. Let's make n 26. Let's make the phase angle 0 and look at n equals 11. Well, we can see that the first spike that's going to appear on the DFT is going to be the positive blue, and that's currently 11. Now if we make it 16, we can see that the first positive spike representing omega 2 is going to be the negative. Okay, so the negative of 16 is 26 minus 16, so that's going to be 10. So we're going to actually see omega 2 first on the left at 10 and omega 1 second at 11 on the DFT. Let's look at the DFT. So if we combine these two stem plots, we'd see omega 2 first at 10. This is its negative. That's its positive. Then we'd see second at 11, we'd see omega 1. That's actually positive and that's negative. So we would stop typically at n equals 13 and not display the mirrored half of it, of the DFT. So we'd actually would see omega 2 first and omega 1, even though if we look at just the positives, this is 11 and 16. This next section forces us to look at this when the number of samples gets larger than 25. So we're actually collecting 2 cycles of data here and 4 cycles of data here. And what we do is we show that the stem plots, the DFT doesn't change. And this drives us into the concept of periodic and non-periodic. And the best way to do that is just to look at this display. If n is 10, that's fine. 9's fine. But if n is 9.5, we see these lumps right in here and here. So it's only periodic when n is an integer. Here we see some fun stuff when omega is 0. That implies n is 1. And we've got the straight line. We started off with n equaling 4. Remember, that's the one where we can see actual patterns. If omega doesn't contain pi, then it's not periodic. There's a slowly slipping or growing pattern. So we're done.